Hello guys and welcome back to Excelsior Academy. So I'm back with the Leninger summary series. So initially we started with the Leninger and in between it got stopped because of certain reasons, personal issues and all. But right now we are back on the track and we are starting with the very first basics topic, that is the water. So the first chapter is the foundation of biochemistry and that is not required because it's just the introduction to biochemistry, like what can come under the portion of the biochemistry. So we'll start the water because many of you think that it's not that important. Guys, this is the most important chapter as part of your biochemistry. And why I'll tell you, because see, when we sit in the interview panel, we are not going to ask the structure of glucose, how glucose is synthesized, what is glycolysis, what is gluconeogenesis. We are not going to ask these direct questions, right? You can expect that at least from us. So what we ask is like more basic, like go back to your 8th and 9th standard or 11th 12th standard, so where we can ask about the molarity questions, based like difference between the molarity and molality. And you might be thinking that these are the very simple questions, but are you able to answer these questions or not? So that's the main question. I'll tell you one from my own experience. So we were sitting in the panel and one of the candidates, so we asked, so that person has gone to Germany for PhD, but because of the health issues, she came back for left her PhD and came back. And then the question was asked, like, what is the molarity of water? She couldn't answer. Can you believe that? Right? So such kind of questions are being asked in the panel. So you guys have to be very thorough with your basics. Now, when I say basics, it is more basics than basics. Okay, so let's do this chapter with full energy. Water. So we know that it is the most abundant substance in the living system and it makes around 70% or more of the weight, most of the weight of the organism. So we know that even for our cell to function properly, we need water. Okay. The first living organism on earth, of course, it was arose in the aqueous solution only. So you know about the oparin, Harlan soup, and we know about the primitive atmosphere, etc., etc. So in short, the life has evolved in water. So the attractive forces between water molecules and the slight tendency of water to ionize are of very importance, crucial importance to the structure and function of the biomolecules. So you see that for example, your fat molecules are hydrophobic, right? They are like water repelling, but at the end of the day, they need this water surrounding system so that they can be catalyzed by the enzymes, because your enzymes are not going to be hydrophobic. They are going to function in the presence of the water, and hence you need the aqueous surrounding. So the water molecule and its ionization products, that is H plus and OH minus, profoundly influence the structure, self-assembly and the properties of all cellular components, including proteins, nucleic acids and lipids. So guys, here I would like to give you a small information that we know that we can write dissociation of water like H plus and OH minus. But when you go out, like for the interview, please do not write like this, because your H plus does not exist like this. It is going to exist like this. So balance the equation, and this is how you are supposed to write if suppose anyone is asking about the dissociation of water. So this is important. Though it is very simple, very basic, but this is important. This is how you're going to answer when everyone is asking about the water dissociation. Okay. So please make this point important. The non-covalent interactions responsible for the strength and the specificity of recognition among biomolecules are decisively influenced by the water properties as a solvent. So this is playing a very important role as the solvent, including its ability to form the hydrogen bonds with itself and with the other solutes. Now this is the property, this hydrogen bonding is the important property of the water, which is enabling the life sustenance on the earth. And we'll see how this is happening. So first one is we are talking about the weak interactions in the ecosystems. So what kind of weak interactions we are talking about? It is the hydrogen bonds. Though it is very weak as compared to the covalent bonds, but this is the most important one. Okay. So hydrogen bonds between water molecules, it provides the cohesive forces, and that make water a liquid at room temperature and crystalline solid at a with a highly ordered arrangement of molecules at the cold temperature. So guys, you know about the capillary action also, right? So this capillary action happens whenever there is a good cohesive forces between the water molecules. Otherwise, you would have not seen any capillary action. Polar biomolecules dissolve readily in water because they can replace the water-water interactions with more energetically favorable water-solute interactions. Are you able to understand this point? This is important. So instead of having water-water interactions, like suppose this is, so here you are going to have the another H, and you are going to have this water-water interactions, right? So instead of this, I'm going to have Na plus, which is surrounded by the water molecules. So this is how it will be surrounded. And this is what is making your salt soluble inside the water. Okay, so यहाँ पे H plus H plus. So this is how it is being interacted. So whenever there is a Na plus, so the O minus is going to have the interactions with the Na plus. If it is Cl minus, then H plus is going to have the interactions. Okay, so this is called the water solute interactions. In contrast, non-polar biomolecules are poorly soluble in water because they interfere with the water-water interactions but are unable to form the water-solute interactions. Okay, so I hope this is clear. Let's move on to the next. Okay. So in aqueous solutions, non-polar molecules tend to cluster together, and that's why we say hydrophobic, right? Like water repelling. So hydrogen bonds, ionic, hydrophobic, and van der Waals interactions, they all collectively call the weak interactions, but collectively they have a very significant influence on the three-dimensional structures of proteins, nucleic acids, polysaccharides, as well as the membrane lipids. So throughout the biochemistry, like in the Leninger's summary series, we are going to talk about these four important biomolecules and how they are present in the aqueous solution or in the non-aqueous solution, and about their functions, their structures, etc. Okay, so this Leninger is going to talk about these four biomolecules. Now, hydrogen bonding gives water its unusual properties. So this is what I was talking about, like water acting as a solvent, a universal solvent, and the end, like best in its action is because of the property of its hydrogen bonding. So water has got the higher melting point, okay, and boiling point, as well as the heat of vaporization than the most of the other common solvents. So if you see the table over here, you can see the melting point of water is 0. I mean, we just now I said it has got the higher melting point, but here it is said the 0. But look at the other solvents, the melting point of there. So methanol has got minus 98. So if I compare with these, the water has got obviously the highest melting point. Look at the boiling point, it is 100. So this we all know, right? With the experience also, like whoever has gone to the kitchen or have used the kettle, so most probably they know the boiling point of water is going to be 100 degrees Celsius. Okay, so these unusual properties are consequence of attractions between the adjacent water molecules that give liquid water a great internal cohesion. So if you see the electron structure of the water molecule, it reveals the cause of these intermolecular attractions. So let's go with the structure of the water molecule. So each hydrogen atom of a water molecule shares an electron pair with the central oxygen atom. Okay, so this is in the case of the carbon bonding. So if you understand this, then it becomes easy to understand the structure of the water molecule also. So let's see the study. Let's just study about the geometry of carbon bonding. Okay, now why I'm discussing this, because these are the basics. This we have already done in our schooling. But of course, like once you go into your higher studies, you tend to forget your basics. So that's okay. That's normal. But you can revise. So carbon atoms have got the characteristic tetrahedral arrangement of their 4 single bonds. So this is the tetrahedral structure. Then it can also have, like in the case of the ethane, right? So you can have over here you have the freedom of rotation over here, like this arrow mark is given. Then the double bonds become more shorter and do not allow the free rotation if it is the double bonded structure. So here it is single bonded. Here you have got the double bonds. So double bonds means because of that, there will be a restriction in the free rotations. Okay. Now the geometry of the molecule is dictated by the shapes of the outer electron orbitals of the oxygen atom, and which is similar to the sp3 bonding orbitals of carbon. Okay. Now this is the electronic structure of your water molecule, and you can see over here oxygen is there, which has got the partial negative charge, whereas the hydrogen is sharing the partial positive charge. So we have got the two hydrogen, right? And then oxygen is having the two pairs of lone pair of electrons, and that's why two partial negative charge is present. So these orbitals describe a rough tetrahedron structure. Now why we say it has got the tetrahedron? See, in the case of carbon, we had got the four, like in the case of the methane, right? So we had the four hydrogen atom over there. I mean, I'm not good with the structure over here, but you can see. So similarly, instead of carbon, we have got the oxygen over here. And instead of the other four hydrogen, we have got two hydrogen here and here. And the rest two is the lone pair of electrons. So in and all, it is also sharing the tetrahedral structure or the tetrahedron. Okay. Okay. So the HOH bond angle is around 104.5. That is 104.5 degree, slightly less than the 109.5 of a perfect tetrahedron. So in the case of the methane, you have got the angle between the HCH, that is 109.5 degree. Now, since this is not the actually the methane, but the water molecule, so the angle is going to be 104.5 degree. Now, this is something, the value which you are going to remember. So, guys, if you're listening to this lecture, please make short notes. As I already mentioned in each slide, what is important to remember. So, here just remember the angle between the HOH, the bond angle. Okay. Yeah. Now, the oxygen nucleus attracts electrons more strongly than does the hydrogen nucleus, and that's why the oxygen is going to be more electronegative. Like already we discussed that it has got the two partial negative charges, right? It means that the shared electrons are more often in the vicinity of the oxygen atom than of the hydrogen. Because of this unequal electron sharing, the two electric dipoles are created in the water molecule, and which is meant for each bond, that is HO bond. Each hydrogen atom is going to have the partial positive charge, and oxygen is going to have the negative charge. So in total, how it is going to be? So as I already mentioned, so H2H are there, right? So partially positive charge, oxygen is there. It is going to have two negative charges. Okay, simple maths. Now, as a result, there is an electrostatic attraction between the oxygen atom of one water molecule and the hydrogen of the another, and hence this form this helps in the formation of the hydrogen bond between the water molecules. So look at the structure over here. So you can see that this is one first your water molecule, and this one is the second. So this is the oxygen over here, and this is the hydrogen. So you can see that in both the cases, this is the angle between the HOH. Right? So the angle is 104.5 degree. Now this is sharing the partial negative charge, and this has got the partial positive charge. Now because of this, it results in the electrostatic attraction, and hence it results in the formation of the hydrogen bond. Okay. So the bond between the H and oxygen is the covalent bond, and the bond between this O and this H is going to be the hydrogen bond. Guys, this one is again important to remember. So you can also remember as 1.7 angstrom. Okay. Easy to remember. Now, so hydrogen bonds are relatively weak. So those in liquid water, they have got the bond dissociation energy of about 23 kilojoules per mole compared to the 470 kilojoules per mole of the covalent OH bond. Okay, so please remember the energy on breaking the hydrogen bond, how much it is released. It is the 23 kilojoules. Now, why I'm saying this is important to remember, because this is what you're going to use when you're going to solve the numericals based on the hydrogen bond dissociation, right? So please remember this. So it is the 10% of the covalent bond due to overlaps in the bonding orbitals, and about the 90% of the electrostatic. So at room temperature, the thermal energy of an aqueous solution is of the same order of magnitude as that of required to break the hydrogen bonds. So when water is heated, the increase in temperature reflects faster motion of individual water molecules, and then that's why it is easy to boil the water. So at any given time, most of the molecules in liquid water are hydrogen bonded. But the lifetime of each hydrogen bond is just to 1 to 20 picoseconds. So when one hydrogen bond breaks, another hydrogen bond forms with the same partner or a new one within zero point 0.1 picoseconds. Can you believe the fastness a water molecule is having? Right? So the apt phrase is flickering clusters has been applied to the short-lived groups of water molecules interlinked by the hydrogen bonds in the liquid water. The sum of all the hydrogen bonds between the water molecules confers the great internal cohesion on the liquid water. So these extended networks of hydrogen bonded water molecules also form bridges between these solutes. So these solutes can be your proteins, nucleic acids, carbohydrates, etc. And that will allow the larger molecules to interact with each other over the distance of several nanometers without physically being touched. So I hope guys you're getting the important points over here. Anyways, I'm mentioning also in between. So the nearly tetrahedral arrangement of the orbitals around the oxygen atom, it allows each water molecule to form the hydrogen bonds with the other four neighboring water molecules. So in liquid water at room temperature and the atmospheric pressure, the water molecules are disorganized and in the continuous motion, right? So each molecules will form the hydrogen bonds with an average of only 3.4 other molecules. This is just an average molecule, average number they have given. Whereas in the case of ice, each water molecule is fixed in space and forms the hydrogen bonds with the full complement of four other water molecules to yield a regular lattice. So this is how your ice lattice is shown. So you can see that each atom is going to be associated with the other four. So if you see, let me make it more clear. So if you take this oxygen, okay, so it is also forming a hydrogen bond with this H. So this is your one interaction. Now this H is making interaction with the other oxygen. So this is second. Hydrogen again making another interaction. Third. And oxygen is making with another hydrogen. So this is four. Now why here two are there? As already discussed that oxygen shares two partial negative charges, right? So in order to balance, it has to require to form hydrogen bonds with two H of the other water molecules. Okay. I hope this is clear. So hydrogen bond account for the relatively high melting point of water already discussed, and because of this much thermal energy is required to break a sufficient portion of the hydrogen bonds to destabilize the crystal atoms of ice. So of course you need more amount of energy to melt the ice. ये तो लेमन को भी पता है. Even if you are not a science student, you know that अगर आपके पास ice है उसको melt करने के लिए you need a good amount of heat energy. Okay, so when ice melts, or water evaporates, heat is taken up by this system. So what is that process? So from solid ice, that is from ice to liquid, it is around taking the energy required is around the 5.9 kilojoules per mole. But from liquid to gas, it is going to take more than that, like 8 times ज़्यादा लेगा वो, so around 44.0 kilojoules per mole. Now again in this, you have to make note of this reaction. Like थोड़ा सा अगर आप इसको याद रख सकते तो that will be more than is sufficient. Now, during melting or evaporation, the entropy of the aqueous system increases as the highly ordered areas of water molecules in ice relax into the less orderly hydrogen bond areas in liquid, and उससे ज्यादा relax इसमें होंगे gas state में. So इसका मतलब क्या? आपका degree of randomness is increasing. Entropy आपका बढ़ रहा है, like from solid to liquid, liquid to gas. So कैसा हो रहा है? जैसे अब ice relax हो गई, उसका system का entropy बढ़ रहा है, right? So what is happening? लिक्विड में जाके वो और लेस ऑर्डर्ड हो जा रहा है. देन अगेन फ्रॉम लिक्विड टू गैस becoming more less ordered, and that's why the degree of randomness increases. So at room temperature, both the melting of ice and the evaporation of water, it occurs spontaneously. So the tendency of the water molecules to associate through hydrogen bond is outweighed by the energetic push towards the randomness. Now, if you remember the free energy change, कैसे देते हैं हम लोग free energy change? Delta G is equal to delta H minus T delta S, right? Delta G हो गया आपको gives free energy, delta H is your enthalpy change, T is the temperature, delta is the entropy change or the change in the randomness. Now, if suppose delta H is positive, then it is going to be, what does it mean? It means the energy has been taken up by the system. जैसे कि in the case of the melting and evaporation, ठीक है? So अगर delta H आपका positive है, so obviously there will be increase in the entropy. जब आपका ये equation में ये बढ़ेगा, so what will happen? Delta G is going to be negative and hence it is going to drive these changes. ठीक है, so जब आपका delta G negative हो जाएगा, so what does it mean? It is going to have the spontaneous reaction. Okay, so wow, पता ही नहीं चला and the topic got over. So guys, that's all for today, and believe me, it was this lecture is going to be helpful because you need to remember the equation. So we talked about the free energy change in the case of the water molecules when it is getting melted from the ice, water, and water to gas में जा रहा है. So you need to remember those delta H, that the enthalpy change you need to remember, and then the equation of the gives free energy, that is delta G is equal to delta H minus T delta S. ये भी आपको याद रखना ही पड़ेगा because throughout your biochemistry portion, whether you talk about protein or you talk about nucleic acid, these equations you are eventually going to use. So keep in mind, please remember, and if you get the numericals, please try to solve it also. So I have also shared many biochemistry numericals. Please go to the playlist of the numericals on the mole bio and biochemistry and practice those questions, because this is going to help in carrying out your research experiments also in future, because you need to prepare your buffers, right? So all these numericals are going to help you guys. So okay guys, thank you for watching the video completely. Please, if you really like the video, hit that like button and subscribe it if you haven't. And any doubts or any suggestions are there, like what topic should be taken first on the priority basis, let me know in your comments. Till then, take care.